Thanks everyone for coming to this session. My name is Aurick. I'm an AI research lead at Snowflake. I'll be talking to you about Arctic Inference, our open source LLM inference optimizations that we've been developing. And this is joint work with a large number of people from the AI research team in Snowflake. Okay, so today, LLM inference systems need to achieve several different goals. They include being responsive, so this means optimizing the prefill speed, which defines how fast the first token responds to your chat application. They need to achieve fast generation, which means that tokens need to stream back as quickly as possible in order to complete the response. And for the operators of the inference system, it also needs to be cost efficient, which means pushing as many tokens through the system as fast as possible. So this is the combined throughput metric. However, a lot of existing systems tend to need to make trade-offs between these goals. Right? And an analogy I like to use is the automobile industry, where gas cars traditionally can be very efficient, but they tend to be a bit slower. Or they can be very fast sports cars, but they are not very efficient in terms of their gas mileage. And it wasn't until electric vehicles came around that broke this trade-off. And it can offer fast speed as well as fuel economy all in one car. So the vision of Arctic Inference is to be the electric vehicle of LLM inference. We want to, at the same time, in the same system, be highly efficient in terms of its combined throughput that's able to push through the system. We want it to also be very fast in terms of responsiveness to the user, as well as the generation speed token after token. So we want all of this in one system. So in pursuit of this goal, we built many different innovations into Arctic Inference that weren't previously published or found anywhere else. We also open sourced all of our research and development, and they're available as a ready-to-deploy system that you can all find on GitHub and use today. So in this talk, I'm just going to briefly cover some of these innovations in Arctic Inference. Those include things like advanced parallelisms, how we optimize for generation latency, how we optimize for batch throughput, as well as a little overview of the open source aspect of Arctic Inference. Okay, so let's jump into the advanced parallelism side. So fundamentally, inference systems are forced into making these trade-offs. One particular reason is due to inflexible parallelisms. So two of the most popular ways to parallelize LLMs across multiple GPUs are what's called tensor parallel and data parallel. So tensor parallelism will take your model and it'll split the model itself across all the GPUs that you have. And whenever a request comes around, it's going to distribute that request across all the GPUs in order to process that request faster. So this is a technique that is really, really good for latency. Each request can complete faster. But it's usually pretty bad for throughput because it incurs more communication costs between the GPUs. So it's basically a bit less efficient, but each response can be returned faster. On the other hand, for data parallelism, what we do is we copy the entire model on each and every GPU that we have. And then for each request that comes our way, we send it to one particular GPU, and that GPU itself is responsible for processing that entire request. So this is a strategy that is good for throughput because there's no communication involved between any GPUs. But it's also bad for latency because each request can only get the power of one GPU to process it. Okay, so as illustrated in the diagram on the right, neither tensor parallelism or data parallelism can really fully achieve the best performance in terms of the combined throughput, the generation latency, as well as the prefill speed. And furthermore, real-world traffic can be bursty. There can be periods of high traffic and periods of low traffic. And this means that the inference system needs to actually dynamically adapt to these patterns as well over time. Okay, so maybe the first approach we can think of is, can we simply just combine these two techniques into one mega parallelism that works for both scenarios, right? And the short answer is no. And the fundamental reason is that they have different KV cache layouts. And KV cache is something, or it's basically some state that needs to be kept in between generating each subsequent token. And data parallelism and tensor parallelism have totally different KV cache layouts, so they cannot really be combined in a straightforward way. So what we do instead is we developed a new type of parallelism called Arctic sequence parallelism, and we use that instead of data parallelism. And how Arctic sequence parallelism is different is that instead of sending individual requests to different GPUs, it sends the different tokens in each request to different GPUs. So one request can have different tokens that go to different GPUs. So this will add some communication overhead to the inference process, but it's actually a lot less than if you were doing full tensor parallelism. And more importantly, the KV cache layout of Arctic sequence parallelism is exactly the same as tensor parallelism. So what this allows us to do is to build what we call shift parallelism. And shift parallelism effectively combines tensor parallelism and Arctic sequence parallelism. Essentially, during low traffic periods, it uses tensor parallelism in order to minimize the latency of each request. And during high traffic, it dynamically switches to using Arctic sequence parallelism in order to maximize the throughput. So by doing this, we're able to break out of the latency and throughput trade-off. Okay, so data parallelism achieves the best throughput, and tensor parallelism achieves the best generation and prefill latencies for each request. Our benchmarks show that shift parallelism can essentially match the latency of tensor parallelism. So it achieves the best latency while it still achieves very high throughput at the same time. What's more is that shift parallelism can adapt to these real-world traffic patterns. And when we benchmarked shift parallelism on this previous example with high traffic and low traffic, it essentially performs the best or close to the best in terms of the response latency, the generation speed, and combined throughput throughout the entire duration of this benchmark. Okay, so next, maybe let's take a deeper dive on what Arctic Inference does to improve generation latency even further. So first, why is generation latency important? So first, recent LLMs tend to think longer. So these are a lot of the reasoning LLMs that are coming out recently. And that means they generate a lot more tokens in order to answer user queries and to achieve higher accuracy results. And second, a lot of agent frameworks actually perform generation many times in a loop in order to complete their tasks. And this can really drag on and lengthen the time that it takes for these agents to respond. And one example is a coding agent that might generate some code and then iteratively refine it and change lines so that it can pass some set of tests. Okay, so to accelerate generation latency, Arctic Inference uses what's called speculative decoding. So normally when we receive a prompt, the LLM will predict one output token, and that output token is going to be fed back into the LLM itself, and then it's going to generate the next token, and so on. And in this process, this is the normal process without speculative decoding. Only one token is generated every time we run the model. With speculative decoding, what we do is we first take a guess at what the next n tokens might be. And then we feed this guess as well as the prompt to the model. And what the model does is it can actually verify how many of these n tokens are correct in parallel. And this allows the model to generate multiple tokens in the same pass through the model. And this can greatly accelerate the generation speed. Okay, so the next question is, how do we actually generate these guesses? And here's where Arctic Inference comes in. What Arctic Inference does is it uses a lightweight speculation model, and this model reuses the hidden states of the large language model in the previous time that it run to predict the tokens for the next time it's going to run. And this is a method that's pretty simple, and we found it to be actually quite effective. So next, for even more effective speculative decoding for agentic applications specifically, we developed a method called Suffix Decoding. And Suffix Decoding is based on this observation that LLM agents oftentimes will generate long runs of repeated text, and these long runs of repeated text can be a lot more easily speculated. And one example that I referred to before is a coding agent might generate new blocks of code in a repeated loop. And each time it generates this block of code, it might only be changing like 1 or 2 lines in that code, right? So the result is highly similar to what it has generated before. So to leverage these inference patterns, what suffix decoding does is it'll index the previous outputs of the model in a very efficient suffix tree data structure in a cache. And it'll use this cache to very aggressively speculate new tokens when it detects that it's starting to repeat. And this approach has several benefits. So first, it can speculate very long sequences. So rather than speculating 2 or 3 tokens in advance, it can speculate tens or hundreds of tokens in advance. And it can also do so very quickly, on the order of around 20 microseconds per token. Okay, so with speculative decoding and suffix decoding, Arctic Inference can boost generation speeds by 2.4 to 4x across a variety of workloads that we tested. And particularly on the left-hand side, we have SweetBench, which is a real-world benchmark in resolving GitHub issues. And this is an agentic benchmark and is one that suffix decoding works especially well on, and we can get up to a 4x speed up on that. We also recently trained speculation models for these new GPT OSS models, and these are the kind of models that tend to generate many, many tokens in reasoning loops. And we showed that we can accelerate the generation for these models from 1.6 to 1.8x. Okay, so maybe a better way to show the speed of Arctic Inference is through like a short demo. So here on the left-hand side, I'm going to play the video in a second, but on the left-hand side, we have the baseline model without any speculative decoding running in vLLM. In the middle, we have speculative decoding using the draft model in Arctic Inference. And on the right-hand side, we also add in suffix decoding. And we assume here that we're doing a very repetitive output, so that suffix decoding already has a large part of the output in its cache. Okay, so let me play that demo. Hopefully this works. I haven't tested. Okay. Okay, so as we can see, the suffix decoding technique is already done, and the normal non-speculative decoding is still running. Okay, so maybe let me see if I can play it again, because I think the right-hand side finished quite quickly. All right, so 3, 2, 1, play. And it's done. All right, so the right-hand side with suffix decoding, so we would only really expect this performance in repetitive output scenarios, which tends to happen a lot in agents, so it can actually greatly help accelerate those cases. All right, moving on. Okay, so next, let's talk a little bit about batch throughput. So batch inference involves running a prompt or many prompts over a large number of documents or database rows. And as you might imagine, this is a use case that's very important for enterprise companies and especially for Snowflake. So some of these use cases include text classification, sentiment detection, summarization, generating a whole bunch of embeddings, and so on. So these use cases are actually not sensitive to latency. They're more sensitive to the total throughput that you can push through the inference system. And another characteristic is that these batch use cases typically process a lot more input tokens than output tokens, right? As you can maybe imagine, the text classification might take in large documents and it'll just output what the class of that document is. And what we actually see in production in Snowflake is around roughly 10 times more input tokens than output tokens. So what this also means is that the previous techniques I talked about, which is speculative decoding, is not going to be very effective here because of the large number of input tokens that need to be processed. Okay, so to optimize the input token throughput, we actually take a different approach, which is called SwiftKV. And intuitively, what it does is it actually changes the model architecture itself of the LLM, so that input tokens only need to run through half the layers of the model. So for example, if this is a LLM that has 6 different layers, all the input tokens will actually only run to the 3rd layer and then stop there, whereas output tokens might go through the entire model. Okay, so if we can achieve this, then it will actually reduce the input token computation by half, which is quite a large margin. But if you actually just try to do this without, if you just try to do this naively, you'll find that the accuracy of the model gets degraded. And what we discover here is that we actually need to do this self-distillation procedure in order to recover the original accuracy of the model. So essentially, the whole process looks like we take some model like Llama 405B or 70B. We apply this transformation to the model so that input tokens can stop after halfway through the model. And then we apply a self-distillation procedure, essentially teaching the model how to mimic its original inputs that it would have original outputs that it would have generated. And we found that by doing this, we can actually recover close to the original accuracy of the model. So here's just some benchmark numbers across a wide spectrum of tasks. And more importantly, for batch inference, using SwiftKV can improve the throughput by up to 2x. And this leads to massive throughput gains and cost savings. Okay, so we also did some work to optimize throughput for embeddings. So embeddings are another very important batch workload, but they often use smaller models and very lightweight models already. So in these cases, the inference overheads usually come from the serving system itself, like a lot of the bookkeeping that might be happening in vLLM or other inference engines. I won't really get into all the technical details here, but we spend a lot of time just optimizing the system itself. And we found that just by doing this, we're able to get pretty massive gains for embedding throughput. So around 4.2 times higher throughput for embedding sequences of length 512, up to 16 times for shorter sequences that are maybe like 50 tokens long. Okay, so a few final words on Arctic Inference and how you can get started. So, in summary, Arctic Inference is a fast and cost-efficient inference system. It combines many of the research innovations that we developed at Snowflake. This includes shift parallelism, speculative decoding, suffix decoding, SwiftKV, the embedding optimizations. And when all of these innovations are combined, it can reduce end-to-end response latency by 3.4x. And improve throughput by 1.7x compared to some of the best and highest performance open source systems out there. Okay, so Arctic Inference is also powering select workloads in Snowflake as well. And the independent benchmarking by artificial analysis showed that the Llama 7dB model in Snowflake is among the fastest among all inference providers in the world. And lastly, of course, Arctic Inference is open source. So it's free for anyone to use, build upon, or deploy. Okay, so getting started with Arctic Inference is really, really easy. I went through a lot of different inference optimizations and research, but I think this is actually one of the coolest parts about Arctic Inference, which is that we built it as a vLLM plugin. And what this means is that you can just install Arctic Inference as a Python package using pip. You specify that you want to use it with vLLM. And then you can just simply launch vLLM as you originally did. For example, using the vLLM serve command. But now this version of vLLM is going to have Arctic Inference optimization flags. For example, to enable shift parallelism, speculative decoding, or SwiftKV. All right, so that's about it. I went through a lot of different optimizations at a very high level. So this QR code up there links to the Arctic Inference repository. It also has links to several papers and blog posts with all the details behind these research innovations. I also has the code to Arctic Inference if you're interested in exploring it. All right, thank you, and happy to take any questions.
The suffix versus speculative decoding you used, those are like two alternative ways to speculate.
Yeah.
I mean, a suffix tree or the helper small model. Do I need to switch between those based on my use case?
Oh, that's a good question. So the question is, there's the speculative decoding based on the lightweight model and the suffix decoding based on suffix tree. And are they alternatives? Do you need to pick between the two and so on? So actually, we figured out a way to combine those. So basically, how it works is that when it detects that there's repetitive sequences, it'll use suffix decoding automatically. And in other cases, it'll fall back to the original speculative decoding method. So from a user's perspective, you typically don't really need to care about, like, do I need to deploy using this suffix decoding configured or not, right? You can just enable both of them, and it will figure out on its own like which one to use during runtime. Yeah.
Very nice talk, thanks. About the suffix generation, decoding, do you know what's the normal footprint of this index?
Yeah. Yeah, that's also a really good question. So the suffix tree data structure itself scales linearly with the number of tokens that it's cached. So it's actually, in terms of memory, it's quite efficient. And the other thing is that this suffix tree cache is stored entirely on CPU memory instead of GPU memory. So usually in where like these serving systems are deployed, all the GPU memory is like taken and like none of the CPU memory is taken, right? So there's actually a lot of free memory usually to hold the cache for the suffix decoding.
Thanks for the presentation, really nice. So two questions. The first one is, does it support all the different quantization schemes out there, essentially supported by LLM compressor? And the second question is about the new parallelization paradigm. Is it dependent on custom kernels development?
Okay, yeah, so good question. So one is it compatible with quantization, different quantization schemes? So we did test many of the techniques with FP8 and FP8 quantization and not quantized, and we haven't really run into any scenarios where quantization is the thing that conflicts with one of these techniques. So they tend to work for us, right? And
Also in the quantization?
sorry?
Also in the quantization, or just floating point?
We tried only floating point quantization. We haven't tried integer quantization, although I can't imagine why that might introduce a conflict. But yeah, we haven't tested that. And sorry, what was the second question?
The new parallelization that is introduced, is it dependent on custom kernels?
Oh, yeah. So is the new shift parallelism dependent on custom kernels? So our current implementation does not leverage custom kernels. It'll use the original matrix multiplication kernels that already comes with vLLM. But I think that there are some opportunities that we could introduce custom kernels and have it run a little bit more efficiently.
Perhaps one last question. Is there any plan to integrate these components in the upstream repository of vLLM?
Okay. Yeah, so are there any plans to integrate it with the upstream vLLM? And the answer is yes. So we have an open RFC and issue open in vLLM, or we're trying to decide the right strategy to do so. I think in Arctic Inference itself, there are certain techniques like suffix decoding or shift parallelism that are general and would benefit the broader vLLM community. And we're working our way to be able to upstream those. Whereas there are some, other techniques that might be a little bit workload dependent, like SwiftKV, where it might make a bit more sense to live out of tree from vLLM. Yeah. Yeah.
Thank you for the talk. Just a question on the suffix-free sort of cache. With speculative decoding, you have like a misprediction penalty, like a draft model divergence on the base model. How is that with the suffix cache? Is it always right, or is there also something?
Yeah. Also a great question. So the question is, for speculative decoding, usually you have a penalty for mispredicting speculated tokens. And for suffix decoding, do you also have that? So the answer is yes. It'll take guesses at tokens, and there will be a penalty for mispredicting tokens. So in suffix decoding, we actually introduced, and you can maybe follow the link and read the paper, which goes through some of this. We have some adaptive mechanisms to try to control for the accuracy of the predictions. And the reason we have that is because if suffix decoding is going to be predicting like 100 tokens at a time, there's going to be like a huge penalty if it is predicting like the second or third token wrong, right? It's going to be spending like 50 times more compute on incorrect tokens. So we introduced some mechanisms to control for that.